pleased to introduce our second speaker for this session, Dr. James Theimer. He is a scientific test and analysis techniques expert currently at Huntington Ingles, working with the Homeland Security Center of Best Practices. Dr. Theimer previously worked for the Air Force Research Laboratory and several predecessor organizations to that one over the course of the last 35 years. He has extensive experience working with modeling and simulations of sensor systems and supporting devices. And his doctoral research was on modeling pulse formation in fiber lasers, which I cannot even conceive what that means. He holds a PhD in electrical engineering from Rensselaer Polytechnic Institute. So let's please welcome our speaker.
Thanks. So yeah, we are the Homeland Security side of the Stat COE at Wright-Patterson Air Force Base. We were given the problem of trying to figure out how do we test systems or how can we be confident that systems will work where we can rarely or perhaps never actually test them. So we investigated that. Several groups had applied Bayesian networks to this problem. So I basically ran through a demonstration case of how you could apply it to a very notional situation, and how you would argue that it had been validated, and to what degree you could argue that it had been validated. And all this is with the goal that somewhere you've got some decision maker who's going to have to get up and say, yeah, it's plausible that this thing actually works, in spite of the fact that we couldn't actually test it, or we could only test it once or twice. So it's Bayesian in the sense that we're using notions of subjective probability, and so that's maybe the biggest Bayesian part of it, at least in what I'm going to talk about. So subjective probability, as opposed to the frequentist view, is it's giving you some sense of what the how plausible it is, if you will, that some parameter or some other some measurable variable takes on a certain range of values. We're going to be looking at a probability of success. So theta is that variable for probability of success. So we could have a straightforward interpretation that the plausibility that it's as a value below P1 is going to be the shaded in region to the left of P1. The plausibility that it's above P0 is the shaded in region above P0. And the examples we're going to be looking at here for convenience sake are beta distributions. They're characterized parameters A and B. A is sort of a how many prior successes you've observed. B are how many prior failures you've observed. So the sum of A and B is sort of an equivalent of how much prior testing you've done, and gives you how confident you are in whatever your number is. So what's the idea of a Bayesian network? It has two parts. You have a directed acyclic graph, which basically gives you the chain of cause and effect. It's directed in that one thing causes another. It's acyclic in that it can't loop back on itself, because that would make figuring out cause and effect really hard. And the nodes have to be described by some conditional probability outputs given the inputs. So I'm looking at this from a digital engineering perspective, that you've asked people developing the system to give you some sort of probability distribution for probability of success for when you run each part of it. And so this would include both the uncertainty due to maybe it just doesn't always work the same way, and it would also include the probability, the uncertainty due to maybe if you did more testing, you could drive down that uncertainty. So the two things are sort of conflated in this picture. And obviously the other thing is you've had to be provided with the directed acyclic graph. Somebody has got this cause and effect chain worked out for you, and you as a teeny person, you're just simply testing it. You're not coming up with it. So we're trying to look at whether it looks plausible in the light of the data you've got and what you can do with it. So I had to come up with a simple notional system. The simplest thing I could come up with is simply reliability, where it either works or it doesn't work. It could become much more complicated than this. You could flow in here in addition to whether it worked or didn't work previously, other factors, other predictor variables, such as environmental conditions and things like that. You could also have other response variables, such as voltages or signal-to-noise ratio, sorts of things like that. But I just needed something relatively simple that I could work with. So what I'm calling reliability nodes are things like nodes 1 and 2, where it's simply said to either work or not work, and where they get combined, I was calling those or nodes for lack of anything better. So it's like if either 1 or 2 works, I say the output of 3 is a 1, a success. If they both fail, I say the output of 3 is going to be a failure. And so the picture is we have n tests with y successes observed for a given test. So basically, this is what I've already said. We have the reliability nodes that have a Bernoulli process with a given probability of success, and the probability of success is characterized by that beta distribution. So there's some uncertainty what that probability of success will be. And the OR nodes, if either one of them works, it's said to work. So for the simulated results, I just produced a whole bunch of sets of size n and just ran them through the network, and I introduced the uncertainty by drawing a new value of theta for each of the reliability nodes every time I generated a new set of n. And that was a way of just simulating it. However, it turned out, because I was generating y samples out of a size n, it had memory, so it was not a simple Markov chain as it's being presented here. So it's not a simple directed acyclic network because the outputs did not depend only on what I have drawn here, but they also depended on some of the input to the prior nodes. So the other way of modeling it was to do it with conditional probabilities. So you would have had to have been given as part of the digital engineering process, the probability of seeing y successes, given that you have I successes on the input. And for the reliability nodes, that is assumed to be a beta binomial distribution. The beta binomial distribution from Bayesian statistics is part of the conjugate family, with the beta describing the uncertainty in theta, and probability of getting y successes is out of n is from the binomial distribution. So again, this is just a matter of convenience. And P of I is the probability of having I successes already in the chain. So at the beginning, I assumed that everything was a success. So you had n successes out of n going into nodes 1 and 2. that gets combined into the OR node, and some of them fail. And so that's how the basically how the what I'm calling the probability nodes were assumed to work. For the OR nodes to make it work as a Bayesian network, I had to get rid of the memory in the system. So I had to build for the OR nodes a sort of a composite node. So the input would have a certain probability vector of the probability of successes for values 0 through n. That would go into two, what I'm calling reliability nodes. Some of them would fail and go into the OR node, and that's how you generate the probability of observing Y successes observed after that composite node. So basically, it's because the order matters that you have to go through this. You could, if the number of successes lined up, they would all be, if they didn't overlap at all, if they never both failed at the same time, then you would have nothing but successes. And it's the fact they don't always overlap that makes the difference. And it can't be if the input to this composite OR node is a failure, it's guaranteed to be a failure going out. If it's a success, it's a matter of did both of them fail going through the probability node. So colleagues worked out for me the equation of what's your probability of observing Y successes on the output given a certain number of successes on the input, and how many successes come out of the two probability nodes in the composite. And by summing up over all that, by running the reliability nodes as reliability nodes with their beta binomial distributions, we could sum all that and get an answer. And so just trying some notional data. Nodes 1 and 2 are the reliability nodes. The input to them was nothing but successes, and you could see, because it's a stochastic process, the probability of observing a certain number of successes declines a little bit. You go into that OR node where it's voting. If either one of them works, it's said to work. So the probability of getting a high number of successes sort of recovers. You go into another reliability node, it declines. You go into 5 and 6, which are two parallel reliability nodes. It declines a little bit. You go into 7, and it recovers a little bit. I'm going to get some disagreement between the two ways I do my computation. And then 7, it declines a little bit. So this is just something to say we have a way of computing the probability of observing Y successes out of N tests on the assumption that I've been given the network and I've been given the probability model, probability of success models for the reliability nodes. So now that I've got that, and this was an example of I was hoping that developing notional data would be easier, but the big takeaway there is that the making your Bayesian network actually function as a Bayesian network can't have wrinkles in situations where there is some memory in the system. I get how to probability of observing Y successes out of N inputs. That's not actually what I want, though. What I want is the probability distribution of the of theta, the probability of success. So I tried fitting the beta binomial distribution to that output, because this is not the output of any given node, but it's of this whole rolled up network, and it fit reasonably well. So from that, I can get an A and a B parameter, and I can use that A and B parameter as characterizing the probability of success of the whole system. And if I can have the PDF of the probability of success of the whole system, I can do all the normal things of computing how plausible it is that probability of success is at least some value. So that's what we're seeing over on the right. I can put into that whatever probability of success is the threshold for which we have to exceed in order for the program to work, and from that I can have, how plausible is it according to this model that the system will work. And this is a situation where I don't have I have models of all the parts. I don't have models of the whole system. And the other thing which I looked at was, does it matter how many simulated observations I have? And it basically seems to be reasonably stable. It's changing some because I'm drawing a different random sample for each time I recompute it. And another thing, as I think I commented before, the model sort of conflates various sorts of uncertainty. It's conflating just does the performance of the system change from run to run, and it's conflating just how much uncertainty is, where if we did more testing, we might be able to refine it. And obviously for probability of success being below a threshold, if the system was actually working better, presumably that probability of being below the threshold would be lower. So this is presenting the decision maker information about how confident he or she can be that it works at least as well as the threshold, but part of that is the system working well, and part of that is do we have the right models? For validation, a proposed way of validating it is simply because we can get a model for Y successes out of N, we can just work out the probability of observing a certain number of successes or fewer. And if we see less than that number, then we can say, well, it would be surprising at a 10% level or a 20% level to have seen that many successes or fewer. It's basically doing a p-value. And obviously this is because I'm showing this for a large number of tests. This might be something you would do on your nodes, on the subsystems, to build up plausibility that if those subsystems are working, the models, of the subsystems are working. How plausible then is it that the model of the entire system is working? So what happens if you can only run one test, which is, after all, the punchline? Well, it does give you this approach, a probability of seeing a given number of successes and a certain number of failures. And in the notional example I've got here, you had something like a 16% chance of seeing a failure. And so here the decision maker would be faced with two decisions, one of which is if it failed and it was, and that's what you saw, and it was going to fail 16% of the time, is that surprising enough for you to reject the model? And the other question is, of course, is 85% probability of success good enough for the decision maker to say, yea, verily, this thing plausibly works? And what happens if we can't test the system at all? Well, we do have the model that lets us roll it all up, and we can fit the beta distribution to that to get the subjective probability of theta. And from that, we do have a picture of how plausible is it that it, in fact, works at least as well as the threshold. And obviously, we could do other statistical tests there. So what's not here Obviously, there were a lot of assumptions that I think I tried to stomp on my way through. We're assuming that the DAG actually does reasonably capture everything, that all the required factors or predictor variables are in the model. We don't have unknown unknowns. We don't have lurking variables or latent variables. And the possible fixes are, as people are running the system, if they can just note how it works, how testing works, how it might change over time or different locations, you might have then some hints that at least your models for the subsystems are not working sufficiently well. And the other thing would be the program would have to be continually interacting with subject matter experts to see is our understanding of how these subsystems work and how they work together changing. And under those conditions, one would hopefully get hints if you're discovering that, look, our knowledge of how these things work has changed over time, and therefore we're going to have to go back to the drawing board. And another comment is simply that over the course of any program, hopefully they're learning more and more about the performance of the subsystems. They're learning more about the performance of the systems. So the whole thing, in a regular digital engineering sense, hopefully would be being refined over time as the program goes on. So this was the solution we were able to come up with to the question of, what happens? Is there anything we can do with situations where we can't test the whole model? And we have you could build the Bayesian network. You could ask them for the things like the probability distributions of the various things you want to measure, and from that you could at least have a plausibility argument for how the system is going to perform. Thank you. Any questions?
Questions for Dr. Theimer?
Hi, I was just wondering how you might incorporate common cause failure into this infrastructure.
Okay, I haven't run into the idea of common cause failure. Can you give me a little explanation?
Maybe something like a manufacturing defect that would affect like your 1 and 2.
Your 1 and 2, yeah.
Environmental features.
Yeah, if it's something where you could carry it as another input, another predictor variable in that DAG, I think you might be able to account for it there. I mean, obviously, if you literally only have parts from that lot, for instance, then yeah, it's going to be like any other statistics thing. It's going to be another lurking variable that if you haven't tested across a number of ones, it would be like another lurking variable where you would just have to look at and see whether are you getting anything that you're surprised by later on. Yes. Well.
Sorry, not sure if it's my turn. I couldn't see the moderator.
Yeah.
I'll happily take it. Question, I understand that you were interested in looking at the question of what could you say if you only had, one piece of data or one observation or even none. Could you actually turn this around, run your model through the other way to address the question, how much data would you need to have at least a certain probability of being able to figure out could the decision maker reach a criterion to say yes or no?
Yeah. I believe you could. I think that if you had, the question might be how much more data would you have to collect? And I think the answer to that is that you could. We've worked on similar things for each of the nodes. And so where it would be, how much data would you have to collect in order to declare that it works at least up to a certain threshold, and that if you had if the Bayesians don't like it when I put it, but if the probability of success, how well, if it works, say, if it actually did work 90% of the time, how much data would you have to collect in order to verify that it works at least, to demonstrate it works at least 80% of the time? Those are calculations that can be done for each of the nodes. And then presumably, I haven't worked how to do this in a non-labor intensive way, but presumably you could then spiral through the network and see how much uncertainty you would have to drive out of the of each of the nodes in order to get the system level, demonstrate the system level performance that the decision maker is concerned about. Mm-hmm. Did that answer the question?
That absolutely does.
Yeah, okay.
I think that would be really interesting.
Yeah, and the other comment, which I did not attack here, but the original application of Bayesian networks was as part of machine learning, so that as you collected more data for each of the nodes, you could be updating the, or even of hunks of the total system, you could be updating your knowledge of the probability of success of those nodes using Bayesian methods. It's just, I was purely looking at it from a T&E point of view and not an updating the understanding of the system point of view.
For Dr. Theimer? Let's thank our speaker.
Thank you very much.